Hello, good morning all. Am I audible?
Yes, sir.
Thank you. Uh, so, in the previous lecture, we probably I think finished the topic on analog instruments, where we discussed the advantage of the analog instruments over the conventional PMMC based instruments. Of course, analog instruments utilize PMMC instrument as the display devices. However, they offer very high input impedance and the feature of extending the range of voltage measurement to lower values of voltage measurement as well, and higher voltage measurement as well. So there we discuss only two types. One is voltage measurement and current measurement. So in today's class we'll discuss about some techniques which are specifically designed for resistance measurement. Of course, we have seen the design of ohm meter, which is the PMC based ohm meter basically is a non-linear device, where non-linear instrument, whereas we also saw that how to extend it to the linear type of resistance measurement, but those approaches are not always feasible, and why they are not feasible we'll also discuss that, and some specific techniques which are designed for only resistance measurement, that will be discussed today. So resistance measurement techniques discussed earlier may not be accurate for very high and very low resistance values. Resistances, okay, and the accuracy is probably is basically affected by the error associated with the voltmeter and ammeter methods which we used previously. So we saw that let's say you have an unknown resistor kept in series with a known resistor, and if you can measure the voltage across this, we saw that probably we can use this approach of voltmeter based method for unknown resistance measurement. That's all we saw, but the voltmeter itself is subjected to errors, right? That is what we also saw. So when we consider voltmeter and ammeter based method, there will be some error associated with that. And the if you see specific resistances, like in the ammeter design, if you remember that we used shunt resistance to take away some part of uh, the meter current, right, which was connected in parallel with that, if you remember, right, to extend the range, current measurement range of the ammeter. So these resistances values were very small, right? So, and the values should also be very precise, because the entire calculation and calibration of the meter is based on the value of RSH. So they are not only small, we need them to be very precise. So when you calibrate the instrument with such resistances, they need to be known very like very accurately. So for that purpose also some specific methods of resistance measurement are required. So we'll discuss that. So let us first discuss what are the problems associated with voltmeter and ammeter method. So one approach is, we have seen that we use this Ohm's law, that R is equal to V by I. Okay, so in some way, if you can measure the voltage across resistance and the current flowing through the resistance, you will be able to measure the resistance. That is a basic fundamental equation which we can use for resistance measurement. So there are two ways. One is voltmeter and ammeter. Two ways of connecting the circuit. One is that you first put the voltmeter in parallel with the unknown resistance. So this is the unknown resistance we are trying to measure. If you put the voltmeter across that, and then the ammeter is connected in series with the arrangement of voltmeter in parallel with the resistance. Okay, but this is one method. Other is you keep the ammeter in series with the resistance to measure the current through it, and connect the voltmeter across the series combination of ammeter and unknown resistance. There are only two ways possible here. Now the simple way is that if you consider them to be ideal ammeter and voltmeter, voltmeter will measure the voltage across R, that is ER, right, and the ammeter will measure the current flowing through the resistance that is I. So ER by I will give you the value of resistance. However, the current which is flowing through the ammeter is getting split into two parts, one flowing through the known resistance, other flowing through the voltmeter. Of course, ideal voltmeter will have resistance of infinity, so there will be any current flowing through this. However, but we have seen that voltmeter do have some finite resistances. So if you consider that resistance as RV, then basically what we are measuring is not R. We are actually measuring RV in parallel with R. Okay, that is what we are measuring. So if you look at the equation of R, the ammeter which is the one which is indicating the current is not indicating the current flowing through R. It is indicating the current flowing through R and the voltmeter, that is I plus IV. The IV is the current component flowing through the voltmeter. I is the current flowing through the resistance. So it is I plus IV which the emitter is measuring. So ideally I should have had this equation, but it has come to this equation because this is the measurement I get from ammeter, this is the measurement I get from voltmeter. So this is fine because it is measuring the voltage across R, but this denominator is not correct. It should have been I, but we are what we have is I plus IV, right? So this is where the resistance measurement goes wrong. Similarly, if you consider another approach that connecting ammeter in series with the resistance, then definitely ammeter will indicate current I only, which is the one which is flowing through resistance. But in this case, we are not measuring the voltage across R by keeping the voltmeter across the series combination of ammeter and resistance. But what we are measuring is the voltage drop across ammeter plus voltage drop across resistance. So here denominator is fine, but the numerator is erroneous, where this extra voltage drop which is coming into picture. What this voltage drop is known as?
Burden
What is it
voltage.
known as? Sorry.
Burden voltage.
Burden voltage, right? So when you but you cannot separate the burden voltage, right? Because it is dependent on the unknown current itself, right? So in that case, you have to uh, deal with the error in resistance measurement, right? So both the approaches, whichever you take, is going to give you incorrect result. Now here I think there is some mistake in the data which is provided for resistance measurement using voltmeter and ammeter. This was actually basically to show you that how the calculation goes wrong when you uh, use the voltmeter and ammeter based method. So let me first find out the actual values which are supposed to be there. I think something is missing here. What is that value? Okay, fine. So okay, so in this configuration, let's say the current measured by the ammeter is 0.5 ampere. Okay, and the voltmeter is measuring 500 volts. Okay, in this configuration I'm talking about figure B, and the ammeter resistance is 10 ohms, quite small, but it is finite. So it is non-zero, and its value is 10 ohm, and the voltmeter which is used has a range of 100 volts with the sensitivity. So I should have mentioned sensitivity of 10 kilovolt kilo ohm per volt. Okay, 10 kilo ohm per volt. So we are asked to calculate the resistance R. Now if you consider this configuration, then what is the value of R you will calculate? What is the value of R you will calculate?
A kilo.
1 kilo.
Sorry?
A kilo. 1 kilo.
1 kilo, right? 1 kilo, that is what you will calculate. But what is the actual value of R?
990.
990.
9
90.
ohm, isn't it? Now, then you can calculate the amount of error associated with the calculated value and the actual value. The actual value of RA is given to us, but probably it is not always known, isn't it? It may also vary depending on manufacturer to manufacturer. So what you have in your hand is only V and I. So 500 divided by 0.5 will give you 1 kilo ohm. But apart from that, you don't have anything. But since we know RA is 10 ohm in this particular case, we can subtract it to calculate the actual value of resistance. Now you use the same thing here, like same values, same voltmeter here, same
Sir,
ammeter here,
general
but
doubt.
in
A
this
general doubt.
configuration. Hello,
Sir, general doubt.
I
So,
have not
sir,
finished.
won't RA be mentioned with an instrument when we buy? So
So
will RA?
just a moment. I will increase the volume. So please.
Sure.
Yeah, yeah,
So
yes.
now can you hear me well?
Yes, yes, please.
Sir, so when we buy the ammeter, won't RA be mentioned with it?
Not always, not always. Plus, it is also subjected to, as I mentioned, if you remember, the temperature and all,
The
isn't it?
temperature.
Right? That may also vary. Right. So not every time you will be able to compensate for the error caused by the ammeter. Okay.
So
Is
not
it?
always. So they won't always give RV.
No, no, no. Means they may give some value, but they will give it with some tolerances, not exact value,
Okay, sir.
because that will also depend on. See, if you manufacture ammeter, right? So we have seen that how ammeters are manufactured. Let's say it is PMMC based one. It has internal resistance associated with the coil plus the shunt resistance. Now these two values are also not exact, right? For all the meters, like say there are 100 meters, not all will have the same RA value, isn't it?
Yes, sir. Yes, sir.
So you cannot use one value to for the purpose of compensation.
So even if they give, there will be some error we have to
Some
take.
error will be there. Definitely there will be some error that will be there. Hmm?
Okay.
So if you try to, of course, like it is always better to have something rather than nothing. So if you calculate the RK value, let's say the actual array is 9 ohm, let's say, but I subtracted 10, but it is still closer to the true value, right?
Yes, sir. Yes.
Yeah. So having knowledge of array is always beneficial, but its value exactly is not known. So this is what is given here. If it is given as 10, then I can certainly subtract it from the calculated value and come closer to the true value. True value, of course, as I mentioned previously also, you can never know. You can never know true value. So, but we are getting closer by this way. Another
Okay.
another approach is this configuration where the voltmeter is connected in parallel with R directly to measure the voltage across that, but the ammeter is connected in series with this parallel combination. So I ammeter is measuring I plus IV. So if I use this example, same values of voltmeter and the current which is measured by the ammeter, then can you calculate the value of R that will be calculated by this in the case of this arrangement? What will be ER in that case? Hmm?
So could
What
you
is
repeat your
yeah
question?
yeah question is now 990 ohm we have calculated in this case, right? In this arrangement.
Yes,
Now
sir.
if I use same voltmeter and ammeter in this arrangement, what will be the value of R that will be calculated?
Here R V is equal to 10 ohm.
Sorry?
Here RV is equal to 10 ohm.
No. How can RV be equal to 10 ohm?
Yeah,
So
uh,
RV is how much? Uh, the sensitivity is 10 kilo ohm per volt. The range is 1000 volts.
10 mega ohm. 10 mega
10
ohm.
mega ohm is RV.
Yes.
RA is same, still 10 ohms. What will be the value? So I'll leave it to you to calculate value of R in this approach
So is
and
the
try to,
measurement of V still the same here? V is
yeah,
still
yeah,
500
measure.
volt measure?
Yes, will remain same. Okay, so I leave it to you to calculate it. Now remember, what our voltmeter is measuring voltage across what value of resistance?
So across R.
No, as I mentioned, it will actually measure the voltage across parallel combination of R, V and R, isn't it?
Yes.
So you please calculate it accordingly and compare it with whatever we have got here, 990, and probably you can comment on which configuration is better for this value of resistance measurement. Okay, see, the one of the approach you have to take, but it depends on the value of R, which is unknown of course, but let's say you have some fair idea that uh, that R lies in this range and it is lower value or very high value. Accordingly, you have to choose which approach is correct in this case. So one way of doing this is practically that you connect the unknown resistance, let's say in this configuration. Okay, first let's say in this configuration, and you do not connect the voltmeter. You do not connect the voltmeter, or let's say you connect the voltmeter first and note down the current reading and voltage reading. Now you disconnect the voltmeter. Disconnect the voltmeter one terminal. So by doing this, what we are making sure that there is no voltmeter current which is flowing through this. So what will happen? Ammeter, whatever reading it was indicating, it will change. The reading will change by a certain extent. If the change is very high, what does it mean? If the change is very high, what does it mean?
RV is significant. The influence of RV is significant.
What does it mean? Significant means what?
It has a very low resistance.
Which one? RV?
RV.
RV? In general, RV is high or low? In general,
it must be high.
it must be high, right? In the design of voltmeter, I will make sure that RV is high. What does it mean?
I mean, it's comparatively low than what we would want.
No. What it means that, see, okay, I will give you an example. Let's say emitter indicated 2 amperes when the voltmeter was connected. Okay, and when you disconnect the voltmeter, let's say it indicated 1.5 ampere. So what does it mean? That the voltmeter was consuming significant current, isn't it?
Yes.
Right. So one way is that one reason maybe is that what you mentioned, RV may be quite low, which is not expected, or RV is comparable with R, isn't it?
That may be so.
Right. RV is comparable with R, so that means R is a quite large value. Right.
Yes, sir, that is
Quite
possible.
large value. That may be
That's
one
also
of the
possible.
reasons.
That's
So
also possible.
yeah, in that case, this circuit is more appropriate for the measurement of R, because in this case, since R is quite high, we know that it is quite high, so I can neglect the effect of RA in this. Okay,
That this should
I
be
can.
appropriate. Then that.
Yeah. So you first observe this. Let's say you choose this circuit, this configuration. Observe the current with the connection with voltmeter, and without the connection with voltmeter. If there is significant deflection, then you should go with this approach. Or if let's say it is 2 ampere before and later on it indicated like 1.99 ampere, it is still closer, so this is fine. That means RV is much greater than R. So this configuration is good enough. Okay.
So I think in this one you'll measure 989.9 instead of 990.
Sorry.
So you said to find out what this for the same values what figure A would give, right? Instead of like figure B gave 1000, but figure A will give 89.9 instead of 990.
So they are almost close, isn't
Yeah.
it? They are almost close, so it is fine. Whichever is there is going to give similar result. But as I mentioned, if the value of R is quite low or quite high, that will depend. That will decide which configuration will give better accuracy. In this particular example, it is not very high also, it is not very low also. That's why we have got similar results for both. Okay, is that fine? Is this understood?
Yes, sir.
Okay. Another approach now, apart from voltmeter ammeter method, another approach is substitution based method, which is also can be taken if you have enough material available with us. So here also you have some fixed voltage E applied across the resistors and ammeter connected in series. Okay. Now here the unknown resistance is first placed, and then you note down the current I which is measured. So let's say IM is a measure current. Okay, some value. We are not bothered about what value it is, some value. Then you connect the precision variable resistors. Precision means its value should be known very precisely and it should be variable. Okay, so for example, a decade box means the resistances are varying. Like you can vary the resistance in the scale of 10, like that, 10 hundreds or something like that, 1 10 100. So it's a decade box. So what you can do is you go on changing the resistance, till the time you observe the same current. You observe the same current. What does it mean? It means that in that case R will be equal to RD. R will be equal to RD. Now here also we are measuring ammeter, isn't it? So will it also have similar problem with associated with this approach, voltmeter ammeter method?
No, sir, because it'll take in account the RA already.
Correct. We are actually compensating the effect of this by considering two experiments, right? One with unknown R and one with known R. Now, what is the limitation of this method?
The precision of the variable resistor.
Exactly. How precisely you can vary. Let's say the resistance of this is 994.5 ohms. Okay. So the decade box will give like 900 plus 90 plus either 4 or 5, right? Either 4 or 5. So either I can measure 994 or 995. If I have a better decade box, let's say, which can go with plus minus point with the precision of 0.1 ohm also, then of course I can get to 994.5. But let's say you have only 3 options. So the minimum is 1 ohm, then 10 ohms, and then 100 ohms. The steps with which you can increase the resistance. So then you have to either go with 994 or 995. In both cases, the error will be 0.5 ohms. So it all depends on how precisely you can vary the resistor. This is the limitation of this, but it is also approach known as substitution method for resistance measurement.
Sir?
Yes.
I have a doubt. So in this, so then to take care of this precision thing, can't we like make like two measurements with the precision variable resistor? So then you'll know, like you calculate with 994 and 995, and then you calculate RA, which you can get precisely, and then you calculate the unknown resistance. Can you do like that?
No. Can you please repeat?
So the problem with the precision variable resistors, you won't get the exact I measured. Like even if you give 994 or 995, you won't.
No. We will not get exact resistance. I have not said exact I measurement.
But why won't you get same I measured? But why will you get the same I measured if the resistance is not the same?
Because that is where, like let's say this has indicated like 1 ampere. Okay. This can never show 1 ampere, not because emitter is faulty. Are you understanding?
Yeah.
It is because the resistance cannot vary with this precision.
Yeah.
Isn't it?
Yeah.
So this problem is associated with the precision resistor, not with the emitter.
Yeah.
Now with this, can you go ahead, like, and what is your idea?
Yeah. So I said that we are not able to get the same I measured. Like we know that the ammeter is not faulty, but because we don't have the same precision in the RD. So what I said was, so then the problem with what you're trying to avoid is the RA, because you don't know RA properly. But using this precision variable resistor, we take two readings and then we get the RA from that, because we know E, right?
Okay. No, but knowledge of RA, how it will help?
Because then you can subtract it from E by I for the figure A.
But how will it improve the accuracy of R? Knowledge of I, how it will improve the accuracy of R? See, in this case, let's say 994 is kept. When 994.5, it indicated 1 milliampere. For 994, it will be slightly higher than 1 milliampere. Slightly higher.
Yes, sir.
When it is 995, it will be slightly lower.
Yeah.
Right?
Yeah.
But you don't know how much. How much of the resistance is causing that? Isn't it?
Why?
Because we have no way of varying it in between.
But we'll get the I precisely, right? Like how much lesser than how much greater.
Again, okay, and here the point of practicality comes into picture. Have you studied current sensitivity? Do you remember current sensitivity of the ammeter? How do we express current sensitivity? Do you remember in the case of PMMC instrument? How do we define current sensitivity? Remember this?
Yeah.
Right. Now this ammeter, let's say at this position, now I have increased the range of the ammeter from microampere to ammeter using some shunt resistances. So let's say it is showing 1 ampere here in this configuration. Now this scale is marked like this, isn't it? Now when we say 1 mm, this distance is 1 mm. Okay.
Yes.
So even the precision with which you can measure the current is also limited. Am I right?
Yeah.
Now when the resistance varies from 994 to 995, and actual value of the current was 994.5, whatever reading is there, it will slightly vary around that time. But if the marker is not marked with very high precision, then we'll not be able to record the change in current. Am I right?
Yeah.
Yeah. So this is where the problem comes. If imagine this variable resistance was a continuous resistor, continuous, not decayed, not in stepwise, it is not increasing. Then at one point you will note the exact same current value.
Yeah.
Why? Because PMMC is a continuously varying, the deflection is continuously varying, right? Even though the scale is marked at discrete locations, the movement is continuous, isn't it?
Yeah.
So if I have a precision resistance which can vary continuously, then one point will reach definitely where it will indicate the exact value.
So you're saying irrespective of the precision of the ammeter?
Irrespective of the precision of the ammeter.
Oh, okay. Okay, makes sense.
It is the discreteness of the variable resistor which is causing the discrete movement of the ammeter pointer of the ammeter.
Oh yeah, yeah. Okay, I get it.
Right?
Yeah.
Yeah. Okay. Okay, fine. So, so apart from this voltmeter ammeter, the most popular way of measuring resistance is basically Wheatstone's bridge. Why it is popular? Have you studied this in 101?
Yes. So we had it in JE. I'm not sure if we studied it like explicitly in another one.
Okay. Wheatstone's bridge is popular because it is null based method. And we know that null instruments are highly accurate, right? Null instruments are highly accurate. In this, what is done is that you have 4 resistances which are placed in 4 branches of the Wheatstone's bridge, and the voltage supply is applied, as you can see. This is supply voltage E, which is applied at these 2 terminals, and all the resistances are precise resistances. Again, precision resistance means its value is known very precisely, and one of them is variable resistor similar to this one, but it need not be a decayed box. You can have a precision resistor over a range which can continuously vary. Okay, you can also use it here also, but here in this case the unknown resistance is placed here. Okay, so here R is unknown. R is unknown. So what is done is you achieve a balance condition. You achieve a balance condition such that you connect a galvanometer. If you remember, galvanometer is nothing but a very highly sensitive PMMC instrument, right? Very high sensitive PMMC instrument, which is connected across the 2 terminals shown here. Now at balance means at balance Ig, that is galvanometer current, is 0. Galvanometer will indicate 0 deflection. What does it mean? When galvanometer is showing 0 deflection, these 2 terminals are at the same potential, right? Same potential. That means the voltage drop across this resistance is equal to voltage drop across this resistance, and the voltage drop across this resistance is equal to voltage drop across the distance. So this is Vp, Vq, this is Vr and Vs. So which is shown here, Vp is equal to Vq and Vr is equal to Vs. But and if you draw the current, so the current supplied here is I. The current drawn from the supply power supply is I, which is getting split into I1 and I2. And then since there is no current flowing through the galvanometer in any direction, remember the direction can be anything depending on the polarity of the voltages, the difference of the between the 2 terminal voltage difference, right? It can flow here or here. So since there is no current flowing through this, Ig is 0, I1 will flow as it is through R, and I2 will flow as it is through S. So the Vp, voltage drop across resistance P, is I1P, and voltage drop across Q is I2Q. Similarly, I1R is the voltage drop across R, I2S is the voltage drop across S. If you substitute these values and take the ratio of this with this, then you get R by P is equal to S by Q. So the unknown resistance R, as you can see, is expressed in terms of known resistances. S, P and Q. Since P and Q is fixed, you have unknown resistance in terms of resistance S, which is variable. So what you are supposed to do is, the moment you place unknown resistance here, uh, you don't know the value of R, so you will have an unbalanced condition where there will be a potential non-zero potential difference, and galvanometer will show some indication, some non-zero deflection, and you vary resistance S to a point that galvanometer indicates zero deflection. There you are achieving the balance condition, and this condition is satisfied. So by knowing the value of S, P and Q, you will be able to calculate the value of resistance R. Okay. Now, as the equation itself says, that the accuracy of the unknown resistance measurement is sum of percentage error in S, P and Q. Now, when we say sum of percentage errors, what does it mean? Which type of error is it? Which
Maximum
type of
possible.
maximum possible error? And if you want to calculate maximum likely error, then
Root of the sum of squares.
yeah. So this, if you now you can see where the application of that whatever topic we discussed that time come here.
Yes.
Like in the evaluation of the accuracy of R with which you can measure, it actually depends on S, the accuracy of S, P and Q itself. So the higher the accuracy of S, P and Q, definitely that will result in high accuracy of the unknown resistance R. The sensitivity of R basically depends on the sensitivity S, like how precisely you can change S. That will actually decide the sensitivity with which can measure. You can see that here the sensitivity and precision basically play the same role in this case. Okay, they basically mean the same thing almost in this context. So, but um, in order to evaluate, so here you can see, we'll take a simple example of the minimum resistance that can be detectable. So even though S you can vary very precisely, okay, galvanometer, as I mentioned, will actually have some finite sensitivity, which is mentioned in terms of microampere per mm, right? So if the galvanometer sensitivity is provided to you, then uh, and of course the galvanometer will also have some finite resistance associated with it. In this case, it is given as 2.5 kilo ohms. One can find out the minimum change that is detectable in R, unknown resistance. Why it is important? Because when we discuss resistance based sensors in the second half of this course, the same technique is used, Wheaton's bridge, just that this unknown resistance is replaced with the sensor, resistive sensor, whose resistance will change depending on the physical parameter we are trying to measure, be it strain, be it temperature, whatever it is. Let's say it is a temperature sensor, the resistance will change with temperature. If you know the minimum change in R that is detectable, that will basically, of course, in that case, galvanometer will be replaced with a voltmeter for measuring the voltage. So that will give us how what is the minimum change in temperature we can measure, right? Because temperature is what is bringing the change in resistance. So minimum change in R that is detectable is basically governed by the parameters E and the Rg value, the galvanometer resistance, or let's say voltmeter resistance later on. So let's take this example and try to find out. For doing that, we need to first evaluate the Thevenin equivalent circuit. Means you have to open circuit the galvanometer from this and come up with an equivalent circuit. So this is V, sorry, I would say V Thevenin, R Thevenin resistance, and this is my Rg. Okay, if I want to evaluate this, now you have already done with like how to calculate Thevenin's equivalent circuit. In this, how will you calculate? You first open circuit VG, the galvanometer, find out the voltage difference. How will you find out what is the voltage difference between these across the galvanometer?
IG into RG.
Sorry.
The current flowing through it into the resistance of it.
No. When you open circuit it, what is the potential difference across these two terminals?
0.
No, I'm not talking about balance condition.
So that will be, I mean, the voltage at, so the voltage at, sir, I mean,
So
sir, I
is
mean,
it
E by,
is it
sir,
VR
E
minus
by,
Vs? Is it VR
sir,
minus
ER
Vs?
times P by R, sir,
Yes,
ER
sir.
times P plus R by E cube, ES by P Q plus S.
So it is VR
Minus.
minus Vs. The
Yes, sir,
voltage
yes.
drop across R minus voltage drop across S. But what is voltage drop across R?
R by
R
P
divided by P
R
plus
plus
R
P.
into
E.
E. And what is Vs?
S by S plus Q into E.
S plus Q into E. And VR minus Vs will give me what? Thevenin equivalent voltage, right? Am I right?
Yes, sir.
Now, what is Thevenin equivalent resistance?
You short the voltage source and take the equivalent resistance across the galvanometer.
Yeah, so you have to short these two terminals. Considering what? Considering that this is the ideal voltage source whose internal resistance is 0. All right. So we are shorting these two. What happens in that case? What is the Thevenin equivalent resistance then? So if I draw the circuit, it becomes like this.
So 3.67 kilo ohm.
No. Tell me in terms of P and R and PQRS.
Q parallel S plus R parallel P.
P parallel
P parallel plus Q parallel S.
P parallel R plus Q parallel S, right?
Yes, sir.
Yeah. So this becomes P parallel R plus Q parallel S. Sorry. Fine. Now try to find the current flowing through the galvanometer. It will be VTH divided by RG plus this combination, isn't it? Am I right?
Yes. Yes, sir.
Now, what is the minimum current that is indicated by the galvanometer? Minimum current. Sensitivity is 1 microampere per mm, right? So 1 microampere is the minimum current that it will indicate, isn't it?
Yes, sir.
So for 1 milliamp, if the galvanometer, like let's say at 0 position, it was here, it deflects by 1 mm to this position corresponding to 1 microampere. That is a minimum current. So that means it is caused by minimal change in R, right? R, let's say, change to R plus delta R, and then galvanometer will indicate 1 microampere. That delta R is the minimum change that has caused that deflection. So if that current Ig is 1 microampere, right? 1 microampere. That means that this VR has actually changed to VR plus delta R, right? Am I correct? Am I right?
Yes,
Or is
sir.
it confusing? When R has changed to R plus delta R, what happens to VR? Tell me, it increases or decreases from the previous value?
It'll increase.
It will increase, right? Now we want to find out how much it is going to increase. We want to find out how much it is going to increase. Now, for 1 microampere of current flowing through the galvanometer, this voltage, see, nothing has changed here. The potential here will remain the same. Since R has changed to R plus delta R, VR is going to change, means it will increase, right? Definitely the potential across this will decrease by the same amount because the potential here will remain the same. The what you can say, how can I put it? Okay, how much is the voltage drop that has occurred across the galvanometer?
2.5
VR
millivolt.
minus VS.
Sorry, no,
2.5 millivolt.
1 microampere into RG. If you do, how much
That
is
is 2.5 millivolt.
2.5 millivolt. Oh, sorry. Okay. How much is that voltage?
2.5
millivolt.
2.5 millivolt. Okay. But in this, when we calculated the Thevenin equivalent resistance, that actually will flow through the Thevenin equivalent resistance also, right? The current which is flowing through the galvanometer, isn't it?
Yes.
So you have to take into consideration the Thevenin equivalent resistance in series with galvanometer. Am I correct?
Yes, sir. That's what.
Right. So in that case, what is the change in the potential difference across the galvanometer? Can someone tell how to go ahead with in calculating? I think should be I think this is too clumsy. Let me go to another slide. Yeah, let me draw it again. So this is my P. Q, R, and S. Fine. R has changed to R plus delta R, which correspond to Ig of 1 microampere. Okay, 1 microampere. So this basically is the voltage difference that has caused VR minus Vs, which is Ig into R, that is R Thevenin into Rg, which is 1 microampere into RTh is how much we have calculated RTh. What is Thevenin equivalent? P parallel R plus Q parallel S. P is given, Q all are given. Can you calculate P parallel R plus Q parallel S?
They're around 3.81.
3.81. You should always mention.
Yeah, kilo.
What is the value? What is the value?
So I did not add RG to it.
Oh, you are not added RG.
Okay, it's 6.31 then, sir.
RG is 2.5 kilo. 0.5 kilo. So it is coming as how much?
6.31 millivolt.
31 millivolts, right? VR minus Vs. you see VR minus VS had changed to 6.31 millivolts due to change in R by delta R, right? When R was equal to R, means previous value, it was at balance, so VR was equal to VS. So VR minus VS was 0, but now it has changed to 6.31 volts. Now we have to calculate that, as I mentioned, VR has increased, right? VR has increased and VP has decreased, isn't it? VR has increased and VP has decreased. So what was the previous VR value? What was VR value previously?
R by R plus P divided by E. I mean, into E.
Can you calculate it?
So that will be nearly 3.636 volt.
Now it has increased to, isn't it?
So what is E? What is the value of E?
E is mention, is it? It's 10 volts.
Okay.
It is 10 volts. Yeah, it is mentioned there. 10 volts. Yeah. So change in R has caused the value of VR to increase from 6.36 3.636 to 6.366 plus 6.31 millivolts. Okay, that much increase it will show. So how much the VR plus delta R is? 6.3 plus 2.00631. How much is it? How much is this?
3.6431.
6.3431. Now this is sorry,
no, sir,
correct?
3.6431.
Oh, sorry, 3.6431. Yeah, thank you. This is the voltage across this after imbalance. What is the voltage across P then? What is the voltage across P?
10 minus 3.6431.
Yeah. So tell me what is P now? New P.
6.3569.
3561.
9.
69. Okay. 3.69 or only 9?
9, sir. 9.
It's correct, yes, sir.
It is 6.9, sir.
6.9. Okay. Now you can actually calculate the current through IP. Current through IP. Sorry, current through P, that is IP. How much is that?
So 1.816 milliampere.
6 milliampere. This IP current, you see, is getting split here. No? How much is going through the galvanometer?
1 microampere.
1 microampere. Subtract it from IP.
1.815 million.
So that is going through R. 1.815
milliampere.
Now you do calculation of R as VR plus delta R divided by IR. How much is this? 3.6431 volt divided by 1.8.
So 2.0072 kilo ohm.
What was previous value of R?
The previous it was 2 kilo ohm.
How much delta R is?
7.2 ohm.
You see, this is the change in resistance. Okay, that is minimally detectable by the Wheaton's bridge. Means if delta R changes to, let's say, 3 ohms, what happens?
it won't detect that change.
Why?
So because it isn't more than 7.2 for it to
No, no,
actually,
no.
I mean, 1
No.
microampere is not flowing through the galvanometer in such a case.
Yeah, it is less than 1 microamp flowing, right? And the meter, let's say if I zoom in the meter part, the scale, let's say the readings are like this. So at 0 position it is here. Unless it shows here, I'm saying that there is no change. But for 3 millivolts, it will lie somewhere here, right?
Yeah, but
But
it'll be
this,
ambiguous because there's no
so we can't
marking.
know. That's why this 1 mm is the minimum change I can detect. Even though it is lying in between, I can't detect it exactly. If I mark it, then definitely I can do that. But without that, that's why this value, whatever we calculated, is the minimum detectable change in resistance, okay, by the Wheaton's bridge. Okay, so Wheaton's bridge is very popular and it has a very wide range of resistance measurement. However, it is seen that it is mentioned in the literature that below 5 ohms, resistance value below 5 ohms are not accurately measured by Wheaton's bridge. You have to modify the Wheaton's bridge, that we'll discuss in the next class. What is the modification that is applied to the Wheaton's bridge to go below 5 ohm for resistance measurement, and for very high resistance measurement like in mega ohms, very high values, which is basically used for insulations and all. Insulators you must have heard about, right? To protect the devices, that resistance values are very high. For that we have special mechanism for resistance measurement. Okay, but in between the values of resistances, Wheaton's bridge is a very popular choice. Okay, and this is how one can do that. So please try to understand Wheaton's bridge carefully, because this will also come in signal conditioning part of the sensors. It is a very useful technique in sensing also, sensing signal conditioning. Okay, so we'll continue in the next class now. Okay, fine. Thank you.
So what will be the pattern for midsem?
Pattern for midsem.
Yes, sir.
Similar to your quiz.
Okay, and also what is the date, or like when?
I think 3rd March. No, your exam is 3rd March. I think.
Okay,
It's the
yeah,
5th, I
because
think.
5th.
there is some
5th March.
PDF being circulated which shows 5th March, sir. But according to the
Whatever I have received, I think it is
slot.
3rd March. No.
Yes, sir.
Okay, I will confirm.
Yes, sir. Yeah.
Anyway, academic section is going to decide the timetable. It is not we who decide the timetable for midsem. Okay, so I think they will let you know. Don't worry about that.
So can you upload the slides?
Yeah, I will upload it now. All including today's class, I will upload it.
Thank you, sir.
Thank you all.